Yes, it is safe to sit inside a car during the lightning. Before moving on to the explanation, let me welcome you to my channel. Today we will discuss about the equipotential surfaces which have a lot of application in our daily life. We will discuss about its properties and how to draw the equipotential surfaces for various charges. Any surface in which all the points on the surface have the same potential, such surfaces are known as equipotential surfaces. These surfaces may be the surface of a body or the surface in space. For example, as we see later on, a charged conductor is an equipotential surface. By joining the lines of constant potential, we can draw the equipotential surface throughout the region where the electric field exists. First property of the equipotential surface. No work has to be done in order to move a test charge over an equipotential surface. This is because of the reason that at every point on the equipotential surface, they are have the constant potential. So as per the equation for work done, work is equal to charge into change in potential. The change in potential will be always equal to 0. Because if you are considering 2 points such that VA and VB, A and B, VA will be equal to VB. Since you are considering the equipotential surface, VA will be equal to VB. As a result, the change in potential VA minus VB is equal to 0. So as per the equation, if potential is 0, definitely the work will be also 0. Second property of equipotential surface. The electric field lines are always normal to the equipotential surface. Suppose if the electric field is not normal to the equipotential surface, in order to move a test charge over the equipotential surface, a work has to be done. But in the case of an equipotential surface, there is no potential differences between any 2 points on the equipotential surface. Consequently, no work has to be done in order to move a charge over the equipotential surface. Therefore, the electric field should be always normal to the equipotential surface. Third property of equipotential surface. The equipotential surfaces are closer in the stronger region and further apart in the region of weaker electric field. As per the relationship between electric field and the potential, electric field is negative gradient of the potential, or E is equal to minus dV by dr. From the equation, it is clear that the electric field is inversely proportional to the distance. So as the distance decreases, the electric field increases. As the distance increases, the electric field decreases. So we can say that it is stronger or it is closer in the region of stronger electric field and it is farther apart in the region of weaker electric field. Fourth property of equipotential surface. No two equipotential surfaces intersect each other. Tangent to the equipotential surface will give the direction of electric potential at that point. So if two equipotential surfaces intersect each other, at the point of intersection we can draw two tangents, which means that at that point the electric potential have two directions, which is impossible. So the equipotential surfaces never intersect each other. We can represent the equipotential surfaces for various system of charges, where the solid lines are used to represent the line of forces or electric field lines, and the dotted lines are used to represent the equipotential surfaces. So first of all, we will represent the equipotential surface for a point charge. Here we can consider a positive point charge. According to the equation of potential, V is equal to 1 by 4 pi epsilon 0 Q divided by R. So V is constant if R is constant. So for a point charge, we can represent the equipotential surfaces as concentric spherical surface. So since it is a spherical surface, the radius will be constant throughout the surface. As a result, the potential will be also constant. Here, the line of force is directing outwards because you are considering the positive charge. So if it is a negative charge, the only difference is that the line of force will be directed inwards. We can draw the same equipotential surface for the negative charge also. That is a concentric spherical surfaces. Now, how to draw the equipotential surface for two equal and opposite charges? That is for an electric dipole. So, here is the representation of equipotential surface for a dipole, where the surfaces are more closer in the region between the charges because the electric field is stronger in that region. Third one is to draw the equipotential surface for two equal positive charges. So this is the way to represent the equipotential surface for two equal positive charges. Here, the equipotential surfaces are farther in the region between the charges because the region is of weaker electric field. Similarly, we can draw the equipotential surface for two negative charges. You can draw the same figure for two negative charges, but the only difference is that the direction of the line of forces will be inwards. The last one is to draw the equipotential surfaces for a uniform electric field. Now, this is a way to represent the equipotential surface for a uniform electric field where the line of forces are parallel straight lines and the equipotential surfaces are the planes perpendicular to the line of forces. Importance of equipotential surface. Like the line of forces, the equipotential surface also gives a visual picture on both the direction and magnitude of the electric field in a region of space. If we draw the equipotential surface at regular intervals of potential, then the equipotential surfaces will be closer in the stronger electric field region and farther apart in the region of weaker electric field. Moreover, the electric field will be always normal to the equipotential surface. When conductors are kept in an external electric field, it shows different properties. The first property is that the net electric field inside the conductor will be always zero. This is because the conductors have a lot of free electrons which is responsible for the conduction. So when the conductors are kept in an external electric field, the free electrons experiences a force which is just opposite to that of the external field. As a result, the free electron moves in the opposite direction of external electric field. This redistribution of charges causes an induced electric field which is opposite in direction of the external electric field but with same magnitude. That means magnitude of the induced electric field is equal to the magnitude of external electric field, but they are in opposite direction. As a result, we can say that the net electric field is zero inside a conductor which is kept in an external electric field. Now comes the second property. Just outside the surfaces or just outside the conductor, the electric field will be always normal to the surface of the conductor. If the electric field is not normal to the surface, there will be a tangential component to the electric field which causes the flow of charges on the surface of the conductor, which causes a surface current. But such currents are not possible under static condition. So you can say that the electric field is always normal to the surface of the conductor. Third property. The excess charge resides over the surface of the conductor and there will be no charge in the interior of the conductor, or the net charge in the interior of the conductor is zero. According to the first property, the net electric field interior of the conductor is zero. If the electric field is zero, there will be no electric flux in the interior of the conductor. So if there is no electric flux, according to Gauss theorem, flux is equal to Q by epsilon 0. If flux is zero, the charge also should be zero. So we can say that the net charge in the interior of the conductor is 0, but the excess charge resides over the surface of the conductor. Now comes the fourth property. The electric potential is constant throughout the conductor. This is because according to the relationship E is equal to minus dV by dr. As the first property, E is equal to 0. So if E is equal to 0, dV by dr should be 0. So differential of a constant is 0. Hence, electric potential is constant. Fifth property. The electric field on the surface is proportional to the surface charge density. So if you are considering a conductor, definitely inside the conductor there will be no charge, there will be no electric field, so there will be no flux. Here, if you are considering the Gaussian surface, the outermost area cross section, there will be a flux, and that flux is equal to E delta S, where Gauss theorem flux is equal to Q by epsilon 0. Q can be replaced as sigma delta S, and flux can be replaced as E delta S. So E delta S is equal to sigma delta S by epsilon 0, where delta S cancels. So E is proportional to the surface charge density. Sixth and last property of the conductor when it is kept in the external electric field. The electric field inside a hollow conductor is 0. So if you are considering a hollow conductor, definitely charge inside the conductor is 0. So if you are considering a Gaussian surface, according to Gauss law, flux is equal to charge by epsilon 0, where charge inside the cavity of the conductor is 0. As a result, the flux becomes 0. So if the flux is equal to 0, the electric field is also 0. Thus, you can say that the electric field inside the cavity of a hollow conductor is 0. Inside the hollow conductor or inside the cavity of a hollow conductor, there will be no electric field. According to Gauss law, the electric flux is equal to Q divided by epsilon 0. That means electric flux depends upon the charge. So if there is no charge, there will be no electric flux. If there is no electric flux, definitely there will be no electric field. So we can say that whatever be the size or shape of the conductor or in whatever electric field it might be placed, the inside the cavity of the conductor there will be no electric field. Or a cavity of a hollow conductor is always shielded from the influence of external electric field, and this phenomenon is known as electrostatic shielding. It is safe to sit inside a car during lightning rather than standing near a tree because car is a hollow conductor. The cavity of the hollow conductor is not influenced by any external electric field. Or we can say that the metallic body of the car behaves like electrostatic shielding from lightning. Now the second application of electrostatic shielding is that the sensitive components of the electronic devices or the sensitive metals are kept inside a metal box where it is shielded from the external electric field. And we will discuss one more application of the electrostatic shielding is that the outer conductor or outer surface of the coaxial cable which carries the signals, which carries the information is grounded. So it is shielded from the external electric field. So you can reduce the loss of signal or loss of information. There are a lot of similar applications for electrostatic shielding in our day-to-day life. So that's all for today. We will meet with yet another important and interesting topic. Thank you for watching me.